Good morning. This is Unit 3, Day 2. We're going to talk about exponential and logistic modeling. So the first one is going to be a model of population. If a population is changing at a constant percentage rate, then our formula is going to be P of T equals, and then our initial population, P sub 0, times 1 plus the rate to the time power. P sub 0 is our initial population. This is very similar to other formulas we're going to work with. Or, of course, is the rate. It has to be in a decimal, not a percentage. If you're given something like 30%, to make it into a decimal, you have to move the decimal spot over twice. So this is 0.3% as a decimal, or sorry, 0.3 is the decimal. And our T is our time in years. So the T is time in years. So if they give you 12 months, that's going to be time as 1 year. Okay, if R is greater than 0, then 1 plus R is growth. If R is less than 0, of course, then it's going to be a decay. So tell whether the population model is an exponential growth or decay function. Find the constant percentage rate of growth or decay. So they give you everything. This one, our circ side, is 1 plus R is the one inside the parentheses. That's 1.025. And this is 1 or 100% plus 0.025. So if we're going to go the other way, if I want to know my actual rate, my percentage rate, I'm going to move it over to the right 2 times this time. So this is the same as 2.5%. And this is growth. It's bigger than 0. This one is 0.92, but this is, inside the parentheses is 1 plus R. So this is 100 or 100% plus, and this would be actually minus, not even 100%. It would be minus 8%. Or it would be 8% decay. Determine the exponential function with the initial value P naught equals 0, or sorry, P naught equals 12. So my initial is 12. My function, I'm going to write this down first, is P of T. My population in respect to time is my initial P sub 0 plus, or times 1 plus my rate to the time. And this is P sub 0, so I'm going to plug this in, 12. 1 plus, my rate is 6% per year, and my 6, I'm going to have to move the decimal spot to the left twice, and if there's nothing there, I'm going to put a 0, so the percentage is 0.06, or 0.06, and my time, it says per year. So this one, we could plug in 1 if we're asked for 1 year, we can plug in 2 if we're asked for 2 years, but this is my function per year. Alright, keep going. Number 3, these are just going to basically be some examples. Suppose the culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 250,000. So this is our function, and we're going to graph it, or we're going to solve it algebraically first. So P of T equals, I'm just going to plug things in. This is 100 bacteria is what we're going to start with. So this is my P naught, or P sub 0, my initial. Oops. I'm going to plug it in. 100. Parentheses, we have 2 Now this says that it doubles every hour. So because it says it doubles, we're going to make this 2. And then every hour, this is going to be to the t power. Now, they're giving us our bacteria is going to be 250,000. So this is our answer. And we want to know what, suppose, predict when the number. So we're trying to find out the time. So this is 250,000. When is it 250,000? So this is going to be kind of new. I'm going to show you how to solve this when we have a power that's an exponent. That's a variable. So we're going to divide by 100. Get rid of this 100 first. Anything that's next to your base, get rid of it. Divided by 100. Just the zeros would cancel, okay? And this is 2,500. So 2,500 equals, this is 1, 2 to the t. Now, after you get the power or the base with the power by itself, you're going to take the log of this number. So we're going to take the log base 2 of this side, and we're going to take the log base 2 of this side, because what happens is the log base 2 of 2 is 1, always. And that's why we have to take the log of this base, whatever this number is, that's the base on this side. So this is going to be t equals, this you're going to put in a calculator. And I think if we put this in our calculator, you're going to get something like 11, I'll show you how to put this in the calculator, 11.287, and this is in hours. Now, to solve this algebraically, we have to graphically, we have to graph it, and it's going to be the same function. So we're going to find out where, in y1 on Desmos, we're going to plug in 100 times 2 to the t. And then, or we can put x here. Especially if you have a graphing calculator, you're going to have to use x and y, right? And then on the y2, or the second one, we're going to put 250,000 and then find out where they equal each other. Where did they touch? So y equals 250,000 is like something like this, right? It's a straight line. Y equals 250,000. And then 100 to the x, I know that goes through 100 on the y-axis. So it goes through this point right here, 0, 100. And it looks like something like this, right? It's exponential, so it goes exponentially. This point right here where they touch, this is my solution, where they intersect. And this point, if you click on it on Desmos, is 11.287, comma, and then it tells you 250,000, obviously. So they don't want to know how much it is, they want to know where. The where is the x value, so this is my where. This is 11.287, and this one is in hours. Okay. Now we're going to radioactive decay. So let's try a problem where it decreases. Suppose the half-life. This is also something that they kind of expect you to know. The half-life means that your rate is going to be 1/2 or 0.5. I use 0.5 usually, but it doesn't matter which one you use. The half-life of a certain radioactive substance is 40 days, and there are 8 grams present initially. So this is my initial P sub 0. Find the time. They're asking you, what is the time? So my time is my variable when there will be 1 gram of substance remaining. So they're giving me my substance, my answer. My base is, my formula is going to be P of t equals P sub 0 times 1 plus R to the t. And my p sub 0, I know, is 8. I know my base is 1 plus r, but it is going to be 1/2. And I know that this is 1/2. Also because this is 1 minus r, which is 1/2, which is 1/2. So this is, I'm going to use 0.5. My p of t equals 8 is my initial times 1/2 to the time, but I know that it is 40 days. So this is going to be divided by 40 because t over 40 is a number of half-lives. So this is going to be t over 40. Now they're trying to ask us what is a time, what is a t, when there will be 1 gram. So this is actually my answer. So my p of t is 1. They're giving me my answer. We can only have one variable. So what I'm going to do is I'm going to show you how to solve this algebraically, and I'm going to show you how to put it into the calculator. So we're going to divide by 8. Remember, divide by anything that's next to your base. Divide by 8. So we have 1 over 8 equals 1/2 to the t over 40. And what we're going to do is we're going to take the log base 1/2 of both sides. Log base 1/2. This is the base of 1 over 8. Log base 1/2 of 1/2 to the t over 40 is just t over 40, always on this side. That's why we use this base for the log, because they'll always cancel. It'll always be 1. It'll always be this exponent. So t over 40 equals log base 1/2 of 1 over 8. You can put this in decimals or your graphic calculator. And then we have to multiply by 40 on both sides. We have to multiply by 40 because it's 40 days. So that's going to be my last step. Make sure the 40 is first, and then you multiply it by the log. That's not part of this expression right here. It's very different. So when you get your answer, you're going to get something like maybe 120. Remember, we're in days. So my rate is going to be 120 days, after 120 days. Alright, now, if you're looking at your calculator, for y1, you're going to put 8. You can put 0.5 or 1/2, put parentheses around it, and then x over 40. If you do your graphic calculator, put y2 where the second one equals 1. This is my solution, 1. And we're going to find out where they touch. It looks something like this. Of course, 1 is like way down here, right? Y equals 1. Now, this part, 8 times 0.5 to the x over 40, looks something like this, and it goes through 0, 8, and it goes through, and it actually does cross this point right here. It goes almost very, very close to the x-axis, never crossing it. Alrighty, this point right here is what we're looking for, this intersection. That's my solution. Where do these touch? Well, this touches right here at 120, 1. So this is after 120 days. This is going to, go ahead and flip your paper over. This is an inhibited growth of cell formula. This is also continuous interest formula. It's the same formula. So for growth, A of t equals my principal, or my initial, which is a sub 0, times e. E is not a variable, it's a number, to the rate times time, or k times t. Okay, it's the same formula. We're going to use this often for interest also. So k is greater than 0. K has to be greater than 0, then we're growing. So this one says, a culture bacterial follows the law of inhibited growth. It's right there. If 500 bacteria are present initially, this is my A sub 0. And there are 800 after 1 hour. They're giving you on that the amount. This is the amount. After 1 hour, this is my time. This will help me find my K. So number one, let's find the K. It's my first step. Plug everything in that we have. My initial amount was 500 times e to the kt equals, they're telling me how much it equals after 1 hour, and that's 800. And I can actually plug in my t also. My t is 1 after 1 hour. Okay, I'm going to simplify this. Always divide by the number in front of the e. Divide by 500. 800 over 500 is like 8 over 5, right? It's the same thing. I'm just going to put 8 over 5 equals, this is 1, e to the k times 1 is k. Now, we're always going to take the log of this number on both sides, but this one is e. Log base e is a special log. It's called a natural log, ln, and your calculator has a special one for it. Natural log of 8 over 5, natural log of e to the k, which is natural log of e. They always cancel out if we have a log with the same base as this base right here. So this is just going to be k equals natural log of 8 over 5. And there's actually a button for that on the calculator. Let me just check it out. So natural log is right here. Natural log of 8 divided by 5 is 0.47. Okay, so this is our interest. So k equals about 0.4700. Okay. This is my interest. This is going to help me with part A. So part A says, how many will be present in the culture after 5 hours? I know my rate now. My initial is staying the same. So this is my second part. This is the one that I'm actually going to use for part A, or to do any of the rest. I found my K. My amount is equal to my initial times e to the kt. I found k. It's 0.47, and they're telling you after 5 hours. It was already in hours, so I don't have to change my units. I already found it in terms of hours. So my amount is equal to, there's no variables on this side anymore. This is just something I can plug into the calculator. 500 e to the 5 times 0.47. And this gives me about 5,242 bacteria. Right? A lot of bacteria. How long before the culture contains 2,000 bacteria? So in this case, you're going to plug it in the opposite way. They're asking how long. So they're asking you, what is T? So 2,000 is my 20,000 is my answer. Equals, my initial is still 500 times E. So the rate is still 0.47. This time, I don't know T. They're asking you T. I want you guys to try this out. Remember, you're going to have to take the natural log of both sides and tell me what you get. T equals what? How long is it? Remember, we're in hours. You may graph it, or you may solve algebraically to find T. Okay, so number 6 is that a chemist has a 100-gram sample of radioactive substance. The table below shows the amount of radioactive material at the end of the week for a 6-week period. And we want to use a graphing utility to fit an exponential function to the data. Okay, so I did this in my calculator. I don't know exactly if I put everything in right, so I want you guys to try it. This is what you're going to do. You're going to go to your calculator. You're going to press stat for statistics. You're going to press 1 for edit. Okay, and we're going to plug everything into this table. You're going to start on this side, L1, and it's going to be 0, press enter. 1, enter, 2, enter, 3, 4, 5, and then 6, right? Press enter after each one. And and then you're going to go to the right, and then we're going to plug in these numbers. 190.4, 76.8, 69.7, 58.2, 49.7, and then 44.2. Press enter after each one, okay? Enter, enter, enter. After each one, not when you're plugging them in. I just plugged in mine already. Now, I'm going to go back to stat. I'm going to go to the right one to calc. And I'm going to go down. I know it's an exponential equation, and I'm going to go down because it tells me it's an exponential function. I'm going to go down until I see something like exponent. I think it's number 8. Let me see. Exponent. Oh, so not linear regression, is exponent regression. And this is 0, actually. So we're going to go to 0. You can press 0, or you can go down to 0 and then press enter. And if you press it, it's going to give you your equation. Okay, so if you're given data in a table like this, it's going to give you your equation. It says A is 102.306. I don't know why it's not 100. That's the initial, but okay. So 102.306. 102.306 times B, which is 0.869. That makes sense. It's less than 1 because we're decreasing to the x. Right? And I think rounding up to 0.869 is fine, to the x. Alright, now I think you guys can use this to find part B, C, and D. Use this function. So y equals this. This is part A. What is the half-life? When will there be 10 grams? That's solving for x. And how much? So this one we're going to plug in 52 and find out how much. I want you guys to try these. If you have any questions, please ask me. This is it. Have a wonderful day.